Okay, good morning. First of all, I would like to thank the organizers to have a possibility to have a talk here. And my name is Simon Mackovjak, and I'm from Slovak Academy of Sciences from Slovakia. And today I would like to present you our results that we prepared with my colleagues and the students. One of them are here, Matej Varga. And the work is called Toward Explanation of Airglow Variation by Machine Learning Techniques. And this work is also supported by European Space Agency, as Slovakia is a European cooperating state now. And I would like to start with the explanation what airglow is. And indeed, airglow is an interface between the space and Earth. And I think, as we talked just a few minutes ago about the cooperation between different fields, and I think that airglow exactly is this interface between the atmospheric science and space science. And I think that we can consider airglow as a display that we can observe what is happening on these altitudes between 80 kilometers to 300 kilometers. And by observation of this emission, we can see the different processes. For example, if the density is increased, that can damage the Starlink satellites, as it was discussed. So it should be seen also in the highest intensity. So therefore, the motivation of this talk is to predict also and to understand these variations that are in the airglow. And the airglow can be effectively observed also from the ground. And here you can see the image from Slovakia, from the Dark Sky Park. And you can see this green line can be also visible from the ground. And now let's imagine that you have a detector that is just looking to this point, and you can measure how this airglow is changing during the nights and during the years. And exactly this instrument was installed in 1960s in Georgia, in the Ombudsman Observatory. And you can see this data that they measured within 1 year. This is the averages per 1 month. And they did it through more than 30 years. And thanks to their very unique data set, we have this information of the green airglow. This is the emission with the wavelength 557 nanometers, originated by atomic oxygen through 3 solar cycles. And you can see that this airglow is very variable. So it's changed from year to year and also through the several decades. And this is not surprise, because as we know, the ionosphere, thermosphere, magnetosphere region is really dynamic. And I would like to just emphasize why it is so. And it is through the different chains that are affected, through the solar radiation chain, through the EUV emission, because mainly the airglow is produced by the EUV photons, and then through the chains of the solar energetic particles and solar wind and magnetosphere chain that heats the atmosphere and also to transmit through the polar regions. But also there are influence of the lower atmosphere and the different processes that are below that can affect the airglow variability. And so our task was that we have these measurements, but it is just 8% of all possible dark nights. And if we can develop a data-driven model that can fill the gaps in the measurements. So we use these airglow measurements as a labels, as a features. We use the available data. So we try to overview and explore all available data for these years. And from them, we selected these 15 parameters. They cover 30 years of observations and have 1 hour step. And as you can see, there are well-known indexes available in OmniWeb. And then there are parameters of thermosphere that can be calculated from this model. And also the ionospheric parameters that can be calculated from the ionospheric model. So we take all these parameters as features, as an inputs, and we try to calculate the outputs, so the airglow intensities. And here you can see the results. So we used several methods for these regression tasks, and the best performance was obtained by the XGBoost, is ensembled method based on random forest. And you can see that for the green line, we have the mean percentage error that is defined like this, something like 16%, and absolute error 88 really. So here is the plot of these results. So the gray points are the measurements, and the dark green line is the model. This is the averages per 2 months. And you can see that these predictions or this model of the XGBoost match quite well. But we also wanted to compare these results with the physical model that is used in this topic for the airglow intensity modeling that's called GLOW. And you can see that it matches also quite well, but it's much more uniform. And this means that this physical model not yet, this can be interpreted as that this model not yet contain all these sources of variations that are embedded already in the data. So here you can see these results of the data-driven model for 1 hour step. And it was published in last year in JGR Space Physics. And also all the code is available on our GitHub, space-lab-sk. So if you are interested, you can reproduce these results by Jupyter notebooks and also with the data. So, but you can maybe ask that, okay, so you did some predictions, but generally you used just the very general indexes, and you would like to predict very local events. Yeah, and actually this is very good questions. And I think that local effects need to be considered for understanding of airglow variations. So therefore, we had an idea to obtain as much data as possible, and to, in the following work, to add it to our model. And as I mentioned before, so the airglow and the thermosphere ionosphere is influenced from above and also from below. So in these few slides, I would like to talk how we consider the influence from above. And we develop a model based on deep learning to automatically segment the structures in the solar corona. So we try to develop it as universal as possible to segment not just coronal holes and active regions, as we did for comparison purposes, but to be universal also to segment other structures. And for this model, we called SCSSNet, so Solar Corona Structure Segmentation Network. And the architecture is based on well-known UNet. And we did several layers to be more robust. And on the input, it is the UV image from AIA SDO. And on the output, we have the segmented structure, in this case, the coronal hole. And we used several datasets for this, and we test also for training and then for testing. And here you can see the results for the test dataset. And the first was the custom that we created with our students through the Zooniverse platform. So we basically created our own labels, but we also used generally available labels from the SPOCA algorithm that are in helioviewer.org, and also the Chimera algorithm that is in the Solar Monitor, and also from the algorithm region growth that is available to observe the sun. And you can see the DICE and IOU metrics for the test dataset of the coronal holes, and the best results are obtained for the region growth. But maybe one note, you can see that the SPOCA has much less values, and we have found that it is mainly due to maybe not that these annotations not cover all the cases of coronal holes. And we found that our model trained better to segment the structures that were the original labels. So therefore, the numbers might be lower. And here you can see the example of this model performance. So on the input, we have image. Here is the ground truth, the mask from the region growth. And here is the prediction. And here you can see overlay. So you can see that the prediction might be even better than the mask if you have enough big data set. And on this bottom panel, you can see how the model performed over the whole data set. So you can see for the over whole year of 2017 that was not used for training or validation. So it's over the 0.8. And on the right side, you can see the comparison of the solar disk area segmented by our model and by region grow. And here is the same example, but for the active regions. So you can see that the performance of our model for active regions is lower, but this is mainly due to, as I mentioned, the problems with the annotations. So indeed, the proper annotations are the main factor for the precision of these models. And these results were also published last year in the monthly notices of Royal Astronomical Society. And the code is also available on our GitHub. So basically, you can find there the notebooks for segmentation of coronal holes and also for active regions. And I know that basically in the same time there were several models developed. I also know that Robert Geraldine has method, and there are some other works. But yeah, I think that they were prepared basically in the same time. And okay, so we can consider this data that we have, for example, for the position of the coronal holes at active regions, and we can incorporate it to our model of airglow. But we would like to incorporate also the influences from below. And there are very intense events like lightnings or TLE events, and they might also influence the airglow variations. And for these reasons, we use the data from the radio measurements of the lightnings in a VLF spectral band up to 30 kilohertz. And basically, this is the electromagnetic pulses that are generated by lightnings, and they propagate through the ionosphere Earth guide hundreds of kilometers. And these instruments are operated by colleagues from Czech Republic, and they can detect more than 10 million of events per year. So this is a very high number of events. And therefore, for this reason, the deep learning approaches are very effective, because what we would like to do is to detect these events and classify them. So as you can see on this upper image, here we have time and here we have frequency. So these lines are the atmospheric, so these are the pulses in the whole range of frequencies. Yeah, and so basically what we did was transfer these images to the tables where you have exact date stamp, and also the characterization, if it is tweak or atmospheric, of how looks like the emission of this. So here you can see the comparison. What we did, there is the tweak with these modes. This is actually the dispersion on the ionosphere, and also what are the characteristics. So our deep learning model based on YOLO 5 was very successful in this detection and classification, and the results were also published, and the source code is available also on our GitHub. And the last work I would like to mention is that we employed machine learning also directly in observation process of TLEs. We have a camera for detection of TLEs, and it as it acquired the data for whole night, so we have more than tens of gigabytes per night. So therefore, we implemented machine learning techniques for automatic data reduction and to allow the autonomous operation of such instrument. So I think machine learning is very effective for that, and you can see more details in this paper. Okay, so our main goal is to become a member of the European Space Weather Service Network, because as you can see, Slovakia is not yet. But I guess that also by using these machine learning techniques, this approach might be beneficial for whole ESA and to Europe. And here's my conclusions, that physics is embedded in the data. So basically, if we would like to gather as much data as possible, we can understand and also to explore the physics that is inside. So therefore, the data-driven model is very useful for that. And in such way, machine learning techniques automate out the research. So we don't need to explore just event by event, but we can explore thousands of events and put them together. So this will be exactly our next steps, to put together all this data that I presented and to recognize sources of airglow variations. So if you are interested in this, you can just write down this link to our GitHub. And the last thing that I would like to say, that if you can, please stand with Ukraine, because it's very terrible there. Thank you very much.